I believe you are doing really amazing, and welcome to this first Principal Thinking YouTube channel. And this is part 4 on permanent magnet. And here we are going to discuss about the unique property of material, which is net magnetic moment per unit volume. But if you not watched part 1, 2 and 3, I request you to go back and watch it and then come back to this video. So in part 2, I have introduced this quantity called magnetic moment, and it is simply multiplication of current times area vector. And how can we find the direction of this quantity is by simply using right hand thumb rule. Now mu is the symbol of magnetic moment as well as permeability constant of any medium, and hence to avoid any confusion many books use small m for magnetic moment, and hence I am going to use a small m for magnetic moment. Now in part 2, what I have told you, magnetic moment of an atoms indirectly related to magnetic field inside the material, but there I have not explained you. So in this video I am going to explain it. Let's ask the question, how does magnetic moment of an atoms are related to magnetic field B inside the material? But before I explain you the role of magnetic moment in permanent magnet material, let me explain you the role of magnetic moment in the solenoid. So what I have done here, I have taken a solenoid which is having total 6 number of turns, and I have assumed arbitrary length L. When I supply the current I, it's going to produce a magnetic field inside the solenoid. And the formula for magnetic field inside the solenoid is simply mu naught times N times supplied current. What is the mu naught? Is the permeability constant of the vacuum, and I is the supply current. But here is the interesting parameter, which is small n, and it is nothing but the total number of turns per unit length. And no matter how big or how small solenoid you have it, in ideal condition the magnetic field B inside the solenoid is going to be the same. Now let's modify this equation. So what I have done here, I have replaced the small n with capital N divided by L, and I just multiplied by area to the numerator and the denominator. We can do that, yes, we can do that. And now the next, what I have done it, I have kept the value of n to 6, and then I just clubbed I and area, and the denominator became now L times area, which is the volume of the solenoid. Now what is the I times area? Just now we have discussed, it's the magnetic moment of individual loops. Now I want you to focus the quantity which is inside the box, and if you see this quantity inside the box, the numerator is the net magnetic moment and the denominator is the volume, and hence we can call it total magnetic moment per unit volume. And now if I have to write the formula for magnetic field inside the solenoid, is simply going to be mu times capital M. Now you will ask me why I am discussing about the solenoid, and let me tell you, the permanent magnet material exactly behave like a solenoid. To explain you this, I have taken the permanent magnet bar here. One is the cylindrical bar and another is the rectangular bar, and any magnets are made of atoms, and inside the permanent magnet every atoms are having magnetic moment because of spinning of unpaired electron, and if it has a net magnetic moment, it's going to be a tiny current loop for every atoms. Now I want you to focus inside the material, not the surface of the material. So current of every atoms is going to be cancelled by the current of its neighboring atoms, and you will see only the net current on the surface which is circulating. And don't you think it is same as the solenoid where currents are circulating on the loops, right? And what we have discussed, the magnetic field in the solenoid is simply a mu naught times the net magnetic moment per unit volume, and hence in this case also, in the permanent magnet case also, the magnetic field inside the material is going to be mu naught times the net magnetic moment per unit volume. Now you will ask the question, how can I find this net magnetic moment per unit volume? And it is very simple. Take a unit volume of any permanent magnet and you just do the vector addition of magnetic moment of every atoms, and you will find the net magnetic moment per unit volume. And if you multiply it by the constant called mu naught, you will get the magnetic field inside the material. Magnetic moment per unit volume is similar to the density where we define mass per unit volume. In other words, we add the individual mass of an atoms and divide by the volume, which is independent of shape and size. And similarly, the net magnetic moment per unit volume is simply the addition of magnetic moment of every atoms divided by volume as density, which is independent of shape and size, and hence the magnetic moment per unit volume is also independent of shape and size. Now, I'm going to tell you a statement which will surprise you. No matter how thick or thin magnet you have taken, the magnetic field inside the magnet is going to be same, because magnetic field is simply multiplication of mu naught and magnetic moment per unit volume. As we know that magnetic moment per unit volume does not depend upon the shape and size, and hence magnetic field in ideal situation, again I am going to explain you what is ideal situation a little later, but magnetic field in ideal situation does not depend upon the size and shape of the material. In other words, the magnetic field inside the thick magnet or thin magnet is going to be same. For your information, magnetic moment per unit volume is also called intensity of magnetization or simply magnetization, and its unit is simply ampere per meter. If I have to answer this question, how does magnetic moment of an atoms are related to magnetic field B inside the material, and the answer is it is not directly related, but it is net magnetic moment per unit volume multiplied by a constant which is mu naught. And here we have described a new parameter or new quantity which is capital M, which is net magnetic moment per unit volume for a permanent magnet material. I was talking about ideal situation in which magnetic field in the thin and the thick material is going to be same, and that ideal situation is nothing but magnet kept in a closed loop iron core. And in this case, where I have taken the thick magnet and here I have taken the thin magnet, in the both case magnetic field inside the magnet is going to be the same. But when you keep this magnet in the air, the magnetic field is going to be different, and which I am going to explain in the next part. But if you're liking this content, please like and subscribe, which will really motivate me, and see you in the next video.